We've discussed the three states of matter, that is, solids, liquids, and gases, and the macroscopic and microscopic differences between them. We're now going to talk about how matter changes from one state to another. We refer to such changes as changes of state, or sometimes as phase changes. Phase changes are always accompanied by energy changes. Matter must gain or lose energy in order to change phase. The schematic diagram you see on your screen explains this. In order for a solid to become a liquid, energy must be added to it to move the particles further apart. The same can be said for the change of a liquid into a gas. As the diagram illustrates, it takes a lot more energy to convert matter from the liquid state to the gaseous state than it does to change matter from the solid state to the liquid state. This is because we have to move the particles much further apart to go from a liquid to a gas than we do to go from a solid to a liquid. That means more energy is required. When a gas turns into a liquid or a liquid turns into a solid, energy is released or removed from the matter. It's important to realize that energy can come in the form of kinetic energy or potential energy. When particles of matter experience a change in kinetic energy on the microscopic level, this corresponds to a change in temperature on the macroscopic level. As we've seen previously, when the kinetic energy of the particles increases and the particles move faster on average, the temperature of the matter rises. When particles move closer together or further apart from each other without changing their speed or kinetic energy, this represents a change in potential energy on the microscopic level. This is what we call a phase change on the macroscopic level. Since particles are attracted to each other, it takes energy to move them further apart from each other, and this energy gets stored as potential energy in the particles. Conversely, when particles move closer together, they lose potential energy, and there is an accompanying phase change. We're now going to spend a few minutes classifying and explaining the various changes of phase that matter can experience. Some of these terms will be familiar to you, while some may not. Now remember that a change of phase or change of state involves matter transitioning or changing from a starting state to an ending state. We'll start with a change of phase known as evaporation. Evaporation is the process whereby particles on the surface of a liquid gain enough kinetic energy to escape the surface and become a gas. This only applies to the particles on the surface. When particles deep beneath the surface change from a liquid into a gas, we call that boiling. But both of these phase changes involve the transition of matter from a liquid state to a gaseous state. In order for the particle on the liquid surface to escape its attraction for the liquid particles beneath it, that particle must gain energy. We can think of evaporation as a cooling process, since liquid particles with the greatest energy escape the liquid surface, leaving behind liquid particles of lower average kinetic energy. Let's take a look at an example, and we'll ask the question, why do we sweat, or why do we perspire? Well, when we perspire, water molecules on the skin surface gain energy from the body and escape the body in gaseous form. Because the energy required to change the water molecules from a liquid into a gas comes from the body itself, when these higher energy gas molecules leave the body, the overall body temperature goes down. Boiling is the process where a liquid turns into a gas at the boiling point temperature. Like evaporation, boiling involves the change in phase from a liquid to a gas, and like evaporation, energy must be added to the liquid molecules to turn them into gaseous molecules. Also, like evaporation, boiling is a cooling process since liquid particles must gain energy to become a gas, leaving behind particles of lower energy on average. But unlike evaporation, when boiling occurs at the boiling point temperature, all the particles in the liquid, not just those on the surface, but all the particles have enough energy to become a gas. Remember that evaporation involves only the surface particles changing phase. So looking at an example here, we ask the question, what's inside of a bubble in a boiling pot of water? So when water is being boiled in a pot and bubbles form, what exactly is inside the bubble? Now, a lot of people will say air is inside the bubble, but think about it. What is boiling? It's the change in phase from a liquid to a gas. So the bubble forms when liquid water turns to gaseous water or steam. So the gas inside the bubble is not air, it's water. It's steam. Condensation is the process where gaseous particles collide with the liquid surface and become part of the liquid, releasing energy in the process. Condensation is really the opposite of evaporation. While in evaporation, liquid particles on the surface gain energy from the particles beneath them to turn into a gas, in condensation, the gas particles above the liquid surface collide with the surface and lose energy to become a liquid again. This energy lost by the colliding particles goes into the liquid, thus warming it. So we can think of condensation as a warming process. Looking at an example here, we're asked, why are humid climates so uncomfortable compared to dry climates in the summer? Well, in answering this question, we see that it's because in humid climates, the gaseous water in the air condenses on your skin and in doing so releases energy to your skin. In dry climates, on the other hand, the rate of evaporation far exceeds that of condensation, so energy gets removed from your body. Okay, remember that with condensation, energy is getting added to your body since it's a warming process. So we'll take a moment to look at a cool demonstration and see how both evaporation and condensation make the dunking bird operate. The toy drinking bird operates by the evaporation of ether inside its body and by the evaporation of water from the outer surface of its head. The lower body contains liquid ether which evaporates rapidly at room temperature. Ether is what we call a volatile liquid which evaporates or turns into a gas at a relatively low temperature. As the liquid ether vaporizes, that is, as it turns from a liquid into a gas, it creates pressure, which pushes ether up the tube. Ether in the upper part of the tube near the head of the bird condenses back into a liquid because the head is cooled by the evaporation of water from the outer felt covering. When the weight of liquid ether in the head is sufficient, the bird pivots forward, takes a drink, and permits the liquid ether to run back to the body. Each pivot wets the felt surface of the beak and head, and the cycle is repeated. Sublimation is the process where particles on the surface of a solid gain enough energy to become a gas directly, without passing through the liquid state. So the phase change involves a solid turning directly into a gas. Of course, energy must be added to the solid for this to happen. And as in the case of evaporation or boiling, sublimation is a cooling process, since solid particles on the surface absorb energy from the particles near them in order to become a gas. Thus, when they escape, the overall energy of the particles that remain is less. Have you ever noticed that ice cubes in your freezer will get smaller in time if they're unused? Why does this happen? Well, you can probably guess that it has something to do with sublimation. Ice cubes in your freezer sublime, allowing solid ice to turn directly into a gas. As the surface particles escape, the solid remaining becomes smaller. So melting is the process whereby a solid turns into a liquid at the melting point temperature. As anyone who has eaten an ice cream cone on a hot summer day well knows, energy must be added to the solid in order for it to turn into a liquid. When melting occurs at the melting point temperature, all the particles have enough energy to enter the liquid state, not just those on the surface of the solid. The melting point temperature of water is 0 degrees Celsius, while the melting point temperature of most metals is many hundreds of degrees Celsius. So in our normal everyday lives, our everyday experiences, we see most metals as being solids. But in order for metallic objects to take the shape of an object that we use in our everyday life, like a car door or paperclip, the metal must first be melted in order to become a liquid so that it can be poured into a mold and take on its desired shape. And lastly, freezing is the process where liquid turns into a solid at the freezing point temperature. Freezing is really the opposite of melting. Melting involves a solid turning into a liquid, whereas freezing involves a liquid turning into a solid. For a given substance, the melting point temperature and freezing point temperature are the same. Since the particles are getting closer together in the freezing process, we would expect that energy must be removed from the liquid in order to freeze it. Have you ever felt the warm air coming out of the back of your refrigerator/freezer? Well, if energy must be removed from liquid water to freeze it, and thus convert it to solid water, which is what happens when your freezer is making ice cubes, where does that energy go? Well, it ultimately ends up in your kitchen in the form of heat. So we're going to look at an example of what we call a heating curve to better understand the above processes that we've just finished describing, as well as the energy changes associated with them. A heating or cooling curve is simply a graph of temperature versus time for a substance that is either heated or cooled at a constant rate. For example, perhaps we take a 1 kilogram sample of ice and heat it on a stove where the burner is set to add heat at a constant rate. When we graph the data, the graph takes on the following shape. That's the shape you see there on the right hand side of your screen. Now, this basic shape would occur for any substance that we heated, not merely water. So how can the shape of the graph be explained? What is the meaning of these flat portions that follow the slope portions? Let's take a closer look at each segment of the graph. So we'll start with the segment AB. Now we'll take a look at how we would describe the change microscopically in terms of what's happening with the particles themselves, and we'll also take a look at how we would describe the process macroscopically. So in the first segment, that is segment AB, this first slope segment, we see that we're adding heat, and that the heat that we add is increasing the kinetic energy of the particles. In other words, we're adding heat and it's making them move faster. That's why the temperature goes up from A to B. Okay, so in terms of energy, the increase in kinetic energy is seen as an increase in temperature. So since our sample starts out as solid water, that is ice, we're bringing up the temperature of that solid water. Now in segment BC, we see this first flat portion. What that tells you is that we're adding heat at a constant rate, yet the temperature is not increasing, right? So what's going on here? Well, here we're adding heat. The amount of heat we add is what we call the latent heat of fusion, and we'll define that in the next slide. But this heat is not increasing the temperature, therefore it's not increasing the kinetic energy of the particles. What's happening to that heat, that energy added? It's going to increasing the potential energy of the particles. And this is what happens during the phase change. This is where the solid ice melts to become a liquid water at the melting point temperature. And remember, we said that what's really going on here microscopically is that we are moving these particles further apart as the solid turns into a liquid, and it takes energy to do that. And the energy added goes into the potential energy that gets stored in those particles. In segment CD, we see once again a sloped section. In this case, we add heat and we're increasing the kinetic energy of the particles, and that's why the temperature goes up. So in the segment CD, all of the ice has melted. It is entirely a liquid now. So now when we add the heat, we're just simply raising the temperature of that liquid water. When we come to the second flat portion, DE, the same thing happens as in segment BC. We're adding energy in the form of heat, yet the kinetic energy is not changing, and that's why there's no change in temperature. So what's happening to that energy add? Once again, it's going to increasing the potential energy of the particles. This is what we call the latent heat of vaporization. It's, as we'll define in the next slide, it's the amount of energy that we need to add to convert our liquid molecules into gaseous molecules. And we said this is associated with a phase change. The liquid water boils to become gaseous water at the boiling point temperature. It takes energy to do that. We've got to move those particles further apart. And finally, in the last segment of the graph, EF, we see once again now that all of our liquids sample has turned into a gas, so we have a pure gas. Now when we add energy in the form of heat, that energy added goes into increasing the kinetic energy of the particles, and that's why the temperature goes up. So let's take a minute to formalize our discussion from the previous slide, because we mentioned the concept of latent heat but didn't really have a chance to define it formally. So let's do that now. In general, when we talk about latent heat, we're talking about the amount of energy that is either added or removed from a substance in order to bring about the phase change. So to be specific here, when we talk about the latent heat of fusion, this is the amount of energy that is needed to change a certain mass of a substance from a solid to a liquid at the melting point temperature, or vice versa. It's the same amount of energy that must be removed from a liquid to convert it to a solid at the melting point temperature. So each substance has a unique value for that latent heat of fusion. And similarly, the latent heat of vaporization is defined to be the amount of energy needed to change a unit mass of a substance from a liquid into a gas at the boiling point temperature, or vice versa, amount of energy removed from the gas to turn it into a liquid at the boiling point temperature. So Once again, for the latent heats of vaporization, each specific substance has a unique value. It has a unique value of energy that is required to bring about that phase change. So let's review and generalize some of these concepts we introduced in the previous slides. Specifically, we're taking a look at the energy changes involved in the calorimetric process. We'll look at these energy changes from both a macroscopic and microscopic perspective. So when we add heat to an object and there's no phase change involved, the heat added simply goes into increasing the temperature of the object. Similarly, when heat leaves an object and there's no phase change involved, the object's temperature drops. When there is a phase change taking place, what happens to that heat that we add? The heat added or the heat removed is required to bring about the necessary phase change. From a microscopic perspective, when heat is added to an object and no phase change takes place, the heat simply increases the kinetic energy of the particles in the object. Remember, that's what temperature measures. It's a measure of the average kinetic energy of the particles that make up an object. Likewise, removing heat from an object when no phase change occurs causes the particles to lose kinetic energy, thus lowering the temperature. So what happens during a phase change? How come heat is added yet the temperature doesn't increase? This is because the heat that gets added goes into increasing the potential energy of the particles. Generally, usually moving them further apart. So remember those flat portions of the heating curve graph. What that suggests is that we're adding energy to our object, yet there is no change in temperature, which means there is no increase in the kinetic energy of the particles. But conservation of energy tells us that if not kinetic energy, it's the potential energy of the particles that is increasing in this case. Okay, we have to basically move those particles further apart. Sometimes we think of that as the process of bond breaking. Likewise, when heat is removed from an object, the temperature doesn't drop during a phase change, and we can say the opposite. Okay, we can say that the particles are losing potential energy in the process of them moving closer together. We think of this as a bond forming process. When it comes to calculating energy changes, when it comes to solving calorimetry problems, when no phase change is involved, and we're simply talking about a temperature change, we use the equation we know and love, Q equals mc delta T. When there is a phase change involved, however, okay, then we're talking about a heat of fusion or a heat of vaporization, in which case we can calculate the amount of heat added by multiplying the mass by the latent heat. Okay, either the latent heat of fusion or the latent heat of vaporization. So finally, let's apply these new concepts to a couple of examples. And in this first example, we're asked, why does a 100 degrees Celsius steam burn hurt more than a burn from boiling water at the same temperature? Perhaps this is something you've noticed if you've ever received a steam burn while lifting the lid off a pot of boiling water, for example. Well, when gaseous water or steam at 100 degrees Celsius condenses into a liquid at 100 degrees Celsius on your skin, the water molecules lose a large amount of potential energy as they get closer together. And we said that this amount of energy lost is what we call the latent heat of vaporization. That energy, that latent heat of vaporization, it gets transferred to your body, causing a burn. So in 100 degrees Celsius boiling water, the water molecules are moving quite fast and certainly those fast-moving liquid water molecules can burn you, but you do not have the added amount of energy being added to your body in the form of this latent heat of vaporization. In the second example, we're asked, how does watering plants before a heavy frost help to protect them? Well, as the outside temperature drops below the freezing point of water, the liquid water molecules on the outside of the plant and soil will lose potential energy as they enter the solid state. This energy, that is the latent heat of fusion, gets transferred to the plant and helps to prevent it from freezing and ultimately causing its cells to burst. So remember how we said that, both condensation and freezing are warming processes, that because the molecules must lose energy to bring about that phase change, that energy has to go somewhere. And in this case, if that energy goes to the plant itself, okay, then it will prevent the plant itself from freezing as quickly. All right, so finally, let's take a look at solving a simple calorimetry problem involving phase changes. In this problem, we're asked how much energy is required to change a 1 kilogram block of ice at negative 20 degrees Celsius to steam at 120 degrees Celsius. So the first step when you get one of these problems is to identify the temperatures where the phase changes occur. In other words, identify the melting and boiling points and see which of these temperatures are going to be important in solving the problem. In this problem, we notice that we're starting out with ice at negative 20 degrees Celsius, and we're ending up with water or steam at 120 degrees Celsius. So in adding heat to this sample of water, okay, starting out as a solid sample, we can see that it's going to experience two phase changes. The melting point of water is 0 degrees Celsius and the boiling point is 100 degrees Celsius. So once we know that, we can see how many steps this problem is going to involve. So the first step, if we're starting it with solid water at minus 20 degrees Celsius, the first step is to figure out how much heat we must add to convert that ice at negative 20 to ice at 0. In this case, there's no phase change. All we're doing is bringing about the temperature change up until the temperature at which the phase change occurs. In this case, the freezing point. So here we're justified in using Q equals MC delta T. Okay, we plug in our values. We're talking about a 1 kilogram object, 1 kilogram sample of ice. We look and we see the specific heat capacity of ice, which, by the way, is different than liquid water and different from steam, is about 2090 joules per kilogram degree Celsius. And our temperature change, we're ending at a final temperature of 0 degrees Celsius, okay, and we're starting at a temperature of negative 20 degrees Celsius. We do the number crunching, and this tells us that 41.8 kilojoules of heat must be added. Next, we have to add heat to bring about the phase change. In other words, we have to add enough heat to convert the 1 kilogram of ice at 0 degrees Celsius to liquid water at the melting point temperature at 0 degrees Celsius. So to figure this out, we use our latent heat of fusion. Okay, the heat added is simply the mass times the latent heat of fusion. Plugging in the numbers, we got 1 kilogram. We look up the latent heat of fusion of water. It has a value of about 3.33 times 10 to the 5th joules per kilogram, which tells us we have to add a total of 333 kilojoules to bring about that phase change. In other words, to be able to melt 1 kilogram of ice. Once we have all of that ice melted and we're now in a liquid state, okay, next we can add heat to bring the water at the melting point at 0 in a liquid form up to liquid water at 100 degrees Celsius. Here there's no phase change, so we use Q equals MC delta T. Once again, we plug in the numbers. Notice that for liquid water, the specific heat capacity is about twice that of what it is for ice. And our temperature change, we're going from the melting point to the boiling point. So we're going from 0 degrees Celsius to 100 degrees Celsius. That takes a total of 418 kilojoules. Next up, we have to basically bring about the phase change. We've got to take the 1 kilogram of liquid water at the boiling point and convert it to gas or steam at the boiling point. Here we can use the latent heat of vaporization. So the total heat added is simply the mass times the latent heat of vaporization. Okay, we take the 1 kilogram, we look up the latent heat of vaporization in a table. It's about 2.26 times 10 to the 6 joules per kilogram. Notice that's much, much higher than the latent heat of fusion. We'll talk about that shortly, for a total amount of heat of 2,260 kilojoules. All right, so finally, we've added enough heat to convert our 1 kilogram sample into steam at 100 degrees Celsius at the boiling point, but we need to bring that steam up to a temperature of 120 degrees Celsius. Since no phase change is involved here, we're simply changing the temperature of the steam. We can use Q equals MC delta T. We plug in the numbers and we come up with an amount of heat added of 40.2 kilojoules. Since the problem asks us to find the total amount of heat that we must add the heat from each of these steps. So doing that, it tells us that a total of 3,093 kilojoules of heat is required to bring ice, 1 kilogram of ice at negative 20 degrees Celsius up to steam at 120 degrees Celsius. If we plot this on a graph, okay, that is, we construct the heating curve, and I did this in graphical analysis, and this is what the graph looks like. You see we have this characteristic cooling curve shape. Okay, you'll see that we have, okay, these flat portions here, okay, where the phase change is taking place. Okay, the slope portions, the 3 slope portions here, okay, and those portions were told then that the heat added goes into changing the temperature of the object. That is the kinetic energy of the particles. So the question is, why are the latent heats of vaporization so much greater than the latent heats of fusion? Okay, generally speaking, remember that the latent heat goes into changing the potential energy of the particles in the object. Okay, and we say that to bring about that phase change, we generally have to move those particles further apart. Remember, what is the difference between a solid and a liquid and a gas? Generally speaking, it's the space between the particles. When we look at the difference in spacing between a solid and a liquid, it's not nearly as great as the difference in spacing between a liquid and a gas. It takes much more energy to be able to move liquid particles far enough apart so that the liquid becomes a gas. It takes much more energy to do that than it does to move particles in a solid far enough apart so that they can be considered a liquid. So that's why latent heats of vaporization are generally so much greater than latent heats of fusion.